Okay, so today we're going to be reviewing some basic chemistry topics, those that may be helpful when we cover some of the more complex chemistry in the class, especially when talking about proteins. So let's start off with atoms, elements. So elements, those are just going to be substances whose atoms all have the same number of protons. Atoms are going to be arranged on the periodic table by the number of protons. So if we look here, we have helium. So helium, its atomic number is 2, meaning it has 2 protons. Now also within its nucleus, along with its protons, you have neutrons. So protons, as you see here, have a positive. So these are positively charged particles. Your neutrons are actually neutrally charged particles. And then around the nucleus, not within the nucleus, but around the nucleus, you have electrons, which have a negative charge. Now, if you look here, the atomic mass of an atom is just going to be the number of protons plus the number of neutrons. So you got 2 protons plus 2 neutrons, making 4. So that's helium. So if we look at the periodic table, we have hydrogen, which is the first atom or element on the periodic table. It's got 1 proton. And fun fact about hydrogen is typically hydrogen will not be found, or at least the majority of hydrogen will not be found with any neutrons in its nucleus. So its atomic mass will be 1. Whereas when we look at helium, it's got 2 protons, 2 neutrons, giving it the atomic mass of 4. And also in nature, if your atom has a neutral charge, if it's not an ion, the number of electrons should equal the amount of protons. All right. So when a neutral or uncharged atom, or a neutral atom, the atomic number, so the number of protons, indicates the number of electrons too. So pretty much just what I said. The atomic mass, that's going to be your protons plus your neutrons. So protons plus neutrons. And then atoms with varying amounts of neutrons, we call those isotopes of an atom. So as we kind of talked about earlier, hydrogen, you've got 1 proton in its nucleus. And because it's not an ion, you have 1 electron within hydrogen, neutrally charged hydrogen. Now if we have an extra neutron, or if we have a neutron in its nucleus, we get deuterium. So that's just going to be hydrogen with a neutron in its nucleus. And then if you have 2 neutrons in its nucleus, we get tritium. So isotopes. So some isotopes are unstable. We call those radioisotopes. So unstable isotopes typically are going to give off energy in the form of light from the nucleus. So we have some uses for radioisotopes. We could use them as radioactive labels to tag proteins to detect their location in the body. Carbon dating is actually a pretty important one. So carbon actually has 6 protons. So if we look at the periodic table, we got carbon. Its atomic number is 6, so it has 6 protons. Its mass is 12, which means in nature, most carbon is going to be, or it's going to have 6 neutrons in its nucleus. Now, there's also another thing called carbon-14 that exists in nature. Carbon-14 is an isotope of carbon that contains 8 neutrons in its nucleus. So carbon-14 is actually formed when rays in the atmosphere, so when we get cosmic rays interacting with nitrogen-14, we actually get the development of carbon-14. But carbon-14 only makes up about 1% of carbon on Earth, whereas your carbon-12, is closer to, 99% of the carbon that we have on Earth. Now, this carbon-14 is taken up by organisms and assimilated. So like, let's say you have CO2 in the atmosphere containing carbon-14. that could be integrated, or sorry, taken up by photosynthesizers, for example. They're going to take CO2 from the atmosphere, splice that together to make sugars. Some of it might be carbon-14. Now, those plants will, assimilate, in a sense, assimilate that carbon-14 into their bodies or into them, the organism, and then maybe they'll be eaten by an herbivore. That herbivore takes in and assimilates that carbon-14, and then maybe a carnivore might take in and assimilate that carbon-14. And so carbon-14 is constantly cycled within an ecosystem. Now the thing is, carbon-14 has a tendency to decay over time through a process called nuclear transmutation. However, its half-life is about 5,000 years. And so if you were living and then died, you would probably have half the amount of carbon-14 in your body about 5,000 years after your death. And so the way we can kind of use the ratio of carbon-12 and carbon-14 to detect the age of things is due to the half-life, the known half-life of carbon-14. So we just look at an organism and we look at the carbon-12 to carbon-14 ratio, and we can give a rough estimate of how old the organism is. We could also use radioisotopes for medical treatment. So if we have, for example, radioiodine, so radioactive iodine, we could inject that into someone with hyperthyroidism or even thyroid cancer. The thyroid will take up that iodine, that radioactive iodine, and then that radioactive iodine will selectively destroy the thyroid and having a lesser impact on the rest of the body. And then we could also use it for medical imagery using radio imaging. So again, the conversion of one chemical element or isotope into another chemical element is a process called nuclear transmutation. So this is going to occur when the number of protons or neutrons change within an atom. Okay, so now let's talk about what makes atoms reactive. So their valence shell is actually what makes them reactive. So if we look here, we have a sodium atom, and its valence shell can contain up to 8 electrons. However, it only has 1 electron in its valence shell. Sodium, its atomic number is 11, so it has 11 protons. Its mass number is 23, and if you remember, to get the atomic number, or sorry, the mass number, we're just adding the protons plus the neutrons. 11 protons plus 12 neutrons is 23. But the valence electrons, that's what's going to make it reactive. So if we go to this example here, your sodium, again, its valence shell can contain up to 8 electrons. Having a valence, or you could say outer shell of electrons full, so if it can fill up its valence shell, it is therefore stable. And so atoms are constantly seeking stability, some form of stability. And in this case, if sodium gives up its electron, it's actually closer to giving up its electron from its valence shell. So it's closer to losing 1 electron than it is to gaining 7, I guess I should say, to make it more stable. So it has a tendency to actually get rid of its electron. So when sodium in nature, or not in nature, makes contact with chlorine, for example, chlorine, if you look at chlorine, it's got 7 electrons in its valence shell. So it's actually closer to just gaining an electron and adding it to its valence shell to get stability than it is to lose 7 electrons. So sodium, once it gets rid of this electron, once it bumps into chlorine, its valence shell actually becomes this shell just underneath the original valence shell. And so then, therefore, sodium becomes stable. So it's lost something, it's lost a negative thing, making it positive. Now it has a positive charge. And positively charged ions, those are cations. So when it gives up its electron to chlorine, for example, chlorine gains a negative thing, so then it accrues a negative charge. So here, sodium and chloride, the chloride ion, which is a type of anion with a negative charge, The disparity in their charge is actually what draws them together. So again, sodium is closer to losing an electron in its valence shell than it is to gaining all 7 electrons, whereas chlorine is actually closer to, or I guess it's a lot easier, it would require less energy to receive a single electron than it would be to lose all 7 of its electrons. And so that's why, sodium and chlorine are pretty good fit, because sodium gives up its electron and chlorine takes it up, making chloride. And so we call this this type of bond an ionic bond. You have this positively charged ion, which is chemically attracted to a negatively charged ion. And so ionic bonds are always going to involve one of the atoms giving up an electron and the other one stealing an electron or receiving its electron. All right, so now let's talk about covalent bonds. So covalent bonds are going to be reactions that occur in which your atoms share their valence electrons rather than completely giving it up and then completely stealing it. So they're going to yield atoms with full valence shells. So if you look at oxygen here, you got 1, 2, 3, 4, 5, 6 electrons in its valence shell. Remember, using sodium or even chlorine as an example, 8 electrons in their valence shell is what gives them stability. Same with oxygen. Now, fun fact about hydrogen, its valence shell, so its outermost electron shell, needs 2 electrons to stabilize it. So this oxygen, which is missing 2 electrons, if it makes contact with 2 hydrogens, both missing 1 electron each, what you can do is you can form a covalent bond in which this hydrogen, so these hydrogens, will share their electrons with oxygen. So this hydrogen now has its valence shell satisfied. This hydrogen has its valence shell satisfied. And now this oxygen has its valence shell satisfied because it's received 2 electrons. So this is a covalent bond where your atoms are sharing electrons.